everybody, welcome back. In this next series of videos, we will investigate the acid and base properties of ions and salts. So let's first check out the bicarbonate polyatomic ion. So in the presence of water, bicarbonate acts as a base. It's a weak base, and therefore water has to act as an acid. Bases, remember, are proton acceptors. Acids are proton donors. And so when bicarbonate accepts a proton, it goes from HCO3 minus to H2CO3. It's accepted a proton, which has a positive charge, so plus minus 1 equals 0. That's why bicarbonic acid is neutral. And then the conjugate base of water is hydroxide after it's lost its proton. Now, when we need to use bicarbonate as a weak base for whatever purpose in our laboratory, we don't just purchase the bicarbonate ion alone. We actually purchase it as a salt. And anytime you hear that word salt, I know you may think of table salt, sodium chloride, and that is true, that is a salt. But from a chemist point of view, a salt is just an ionic compound. So therefore, we can't purchase bicarbonate as a polyatomic on its own. It's purchased as a salt. Now, that sodium ion is neither acidic nor basic. Which means it does not ionize water. It's not going to change the pH or the level of hydronium ions versus the level of hydroxide ions. But the bicarbonate ion acts as a weak base and thus has a pH less than 7. And in a future video, I will discuss cations and sodium ion in particular later on. But in this video, I'm going to look at anions as weak bases. So if you have an anion that is the conjugate base of a weak acid, it is itself a weak base. So we see here that bicarbonate is the conjugate base of carbonic acid. Those are the conjugate acid-base pair right there. And carbonic acid's not on the list of strong acids, so therefore it is a weak acid. An anion, that is the conjugate base of a weak acid, is itself a weak base. And so therefore, when I purchase sodium bicarbonate, which is baking soda by the way, and I mix it with water, if I were to measure the pH, it should be basic in the solution. Now, if you have an anion that is the conjugate base of a strong acid, it is pH neutral. So conjugate base of a weak acid is a weak base, and therefore the solution would be basic if it's paired with a neutral cation. And like I said, I'll discuss cations in a later video. An anion that is the conjugate base of a strong acid is pH neutral. Let's look at a couple of acids and their conjugate bases here to make this more clear. So we know that hydrofluoric acid is a weak acid. We've discussed how that strong bond, even though fluorine is so electronegative, doesn't really want to let go of that proton. So it's in equilibrium. The conjugate base of hydrofluoric acid is fluoride after it's lost its proton. And then the conjugate acid of water, when it's gained a proton, is the hydronium ion. Now, if we focus on the conjugate acid-base pair here, has water in it, so the weak acid. This fluoride is the conjugate base, so it's a weak base. Remember, acids, proton donor. Bases are proton acceptors. And the key here is that if it's a weak acid, weak base, we have equilibrium arrows, which means the reaction goes forward and it goes back in reverse. And so you can imagine here that yes, HF is willing to donate its proton to a small extent, but fluoride is just as willing to accept a proton to go backwards, right? So they are acting as a weak acid donating proton and a weak base going back and accepting that proton. Whereas if we were looking at hydrochloric acid, which is one of the strong acids, in comparison, strong acids dissociate completely, so there's no arrow going back in reverse. So complete dissociation. Therefore, we have a strong acid, and the chloride is the conjugate base, but it has no affinity for protons. And thus is neutral. Remember, what affects the pH of a solution is the concentration of the hydronium ions in solution. That's how we measure pH relative to the concentration of hydroxide ions in the solution. Now, fluoride will take protons, right? And therefore, it will affect the concentration of the hydronium ions in solution and thus affect the pH. And so that's why if you have fluoride by itself, then it will act as a weak base and make the solution basic. So for example, sodium fluoride would create a basic solution. Sodium being an ion that's neutral, not going to affect the pH. Now with chloride, since hydrochloric acid is such a strong acid, it's going to lose its proton and say, I don't want it back, right? There's no arrow going in reverse. And so that shows that since chloride is the conjugate base of that strong acid, it has no affinity for the protons. It's not going to try to accept a proton back, and therefore it's not going to change the level of hydronium ion solution, and therefore it won't affect the pH. And that's why we say chloride is pH neutral. I want to indicate that it's pH neutral. Never want to indicate that it's just neutral because obviously it has a -1 formal charge there. All right, so in review, anion, that is a conjugate base of a weak acid, is itself a weak base. And an anion that is the conjugate base of a strong acid is itself a pH neutral. Now, the huge mantra, and it's written very small here, but I want to just highlight it here. A lot of times you're asked to rank acids in terms of strength, or even bases in terms of their strength. And I always found it useful to understand the strength of the acid and focus on acids themselves. So when I were asked about bases, I know what they are relative to the acid. And the reason why that is that the stronger the acid, the weaker its conjugate base. So for example, I know that hydrochloric acid is a strong acid, so then I know that its conjugate base is so weak, right? It's the opposite. Whereas I know ammonium is a pretty weak acid, right? And therefore its conjugate base must be stronger relative to chloride. And indeed it is, right? That's ammonia. It's a relatively strong compared to chloride. Still a weak base, but like I said, it's all relative to one another. Water is a very weak acid, but its conjugate base, hydroxide, is considered one of the strong bases. So for me, it was always easier to understand the strength of acids relative to one another based on structure-property relationships. And if I was ever asked to rank bases in terms of their strength relative to one another, I would always go back and think about their conjugate acid and then rank the acids. And then my mantra was always, the stronger the acid, the weaker its conjugate base. So let's go ahead and work a problem together to make sure we understand at least identifying if an anion will be basic or pH neutral. So we look at the first one here, and it's an anion. It's the conjugate base of some acid. It's an acid that many of you may not know. It's actually the conjugate base of benzoic acid. And so I will actually show the organic structure for fun. No worries, you're not required in my general chemistry course to do the electron flow, but I think it'll make a nice visualization for you all. And so we know, like, even if we don't know what the acid is, we know it's not one of the strong acids, right? It's not hydrochloric acid or hydrobromic or hydroiodic. It's not nitric, it's not perchloric, nor is it sulfuric acid. So if it's not one of those, we can assume it's coming from a weak acid itself. And the conjugate base of a weak acid turns out to be a weak base. So if we purchase this conjugate base, which is going to be called benzoate, we don't purchase it as the anion, we'd purchase it as like sodium benzoate. It would make a basic solution since sodium's not going to affect the pH itself. And if we look at iodide, iodide's the conjugate base of what? Of hydroiodic acid, and that is a strong acid. And so it is pH neutral. So for part A, we would expect it to be basic. And for part B, we would expect it to be pH neutral. I'm going to go ahead and draw the structure for benzoic acid so that you can see what's going on here. Benzoic acid has a benzene ring with a carboxylic acid attached to it. Now I'm going to work with the conjugate base of that. That's the benzoate. And then in the presence of water, remember the base is a proton acceptor. So these electrons here are going to grab this proton, and then this is going to break this bond and push those electrons up onto the oxygen there. Now this is going to be a weak base, so therefore we need to use the equilibria arrows. Now this oxygen has two lone pairs, and now it has a new bond between oxygen and hydrogen. And we're left with the conjugate base of water, which is hydroxide, which has a -1 formal charge. And so you can see here that this weak base can accept a proton. Basically, it can ionize water. That's what I mean by ionizing water, is that it's going to create the hydroxide ion. It's going to fluctuate and kind of increase the amount of hydroxide ions in solution, which is going to make the solution basic if there's nothing else in there to counteract this ionization. And then it produces the conjugate acid of benzoate, which is benzoic acid. Now, if you wanted to write this in a general chemistry format, you can just write the formula. So this was C7H5O2 minus plus water to give you C7H6O2. You're adding a positive charge, so even if you didn't know the structure of benzoic acid and the fact that it was neutral, just make sure you add up the charges correctly, and then plus hydroxide. It's the conjugate base. So that's what's going on here with the benzoate anion. And then if you looked at the iodide, well, we can actually show iodide as the other form because it's not going to accept a proton. That reaction's not going to proceed in that direction. But if we were to just investigate the hydroiodic acid in the presence of water, to indicate that the iodide is not a good base, we would show just a single arrow going forward. You have the iodide plus we have the hydronium ion here. You weren't required to draw this. You were only required to write the equation that shows the anion acting as a base, right? But we can't show an equation of iodide acting as a base because it will not go back towards that direction. And so this is just showing that once hydroiodic acid donates its proton, it's not going back. So therefore iodide is pH neutral. All right, thank you all for watching, and I'll see you next time.